guys, my name is Lina Mwakitawa and I'll be taking you through multiplicative inverse from where my colleague left. Multiplicative inverse is an integer v such that v is equals to 1 modulo n. For example, 5 is a multiplicative inverse of 2 modulo 9 because 2 times 5 congruence 1 modulo 9. Another example, 1 is a multiplicative inverse of 19 modulo 9 because 1 times 19 congruence 1 modulo 9. When you take 1 times 19, you get 19. Then when you subtract 1, get 18. 18 divided by 9, that is 2, meaning that is congruent. There are integers a and positive integers n that do not have a multiplicative inverse modulo 9. For example, 3v is equals to 1 mod 9. This congruence can be equivalent to the following statement. 3v is equals to 1 plus 9k for some integer, which is k in this case. However, the left-hand side of this equation is divisible by 9, but the right-hand side is not. This is because 3 is a factor of 9k, so 1 plus 9k is 1 more than the multiple of 3. This is impossible, and so 3 does not have a multiplicative inverse modulo 9. Because in this statement, there are those which have multiplicative inverse and those which do not have, such as this case we've seen. We can say that any integer that shares a common factor other than 1 with a 9 above doesn't have a multiplicative inverse modulo 9. Two integers whose highest common factor is 1 are said to be coprime. If a and 9 are coprime integers, then a does have a multiplicative inverse modulo 9. From Bézout identity, which we've learned earlier, if the highest common factor of a and 9 is 1, then there are integers v and w such that av plus 9w is equals to 1. Therefore, av is equals to 1 minus 9w. That is Bézout identity. From the method of writing a congruence as an equation in reverse, we see that av congruence 1 modulo 9. Therefore, v is a multiplicative inverse of a modulo 9. Rules for existence to see where if there are multiplicative inverses modulo n in situations. One rule, if the integers a and n are coprime, then there is a multiplicative inverse of a modulo n. If a and n are not coprime, then there is not a multiplicative inverse of a modulo n. This is to say that for any equation or any congruence to say that it has a multiplicative inverse, it has to have a and n as coprimes. When asked to find a multiplicative inverse modulo n, it is usually clearest to give the least residue. We learned least residue in previous chapters. When n is large, we can find multiplicative inverses by using Euclid's algorithm and backward substitution. Euclid's algorithm we learned earlier in the topic. For example, we are asked to find multiplicative inverse modulo n. You determine whether a multiplicative inverse of a modulo n exists, and if it does, find 1. The question is a. We have a as 5 and n as 13. The first thing to do is first check whether 5 and 13 are coprime. In this case, they are coprime because they are both prime numbers. Since we've said that we can use numbers which are less than 13, try the values 1, 2, 3 onwards up to less than 13, one by one, until you find the multiplicative inverse modulo 13. In this one, you can find 5 times 1, 5 times 2, 5 times 3, and so on, until we reach to 5 times 8, whereby 5 times 8 is 14, congruence 1 modulo 13. We can stop there as we have found that integer v such that 5v is congruent 1 modulo 13. So 8 is a multiplicative inverse of 5 modulo 13. A shortcut for this is that we saw that 5 times 5 in the equation of 5 times 5, congruence 12, congruence negative 1 mod 13. So negative 5 times 5, congruence negative 12, congruence 1 modulo 13. Since negative 5 is congruence 8 modulo 13, it follows that a multiplicative inverse of 5 modulo 13 is 8. This is a shortcut for it. Instead of going times 8 times 1, yeah. Another question using the Euclid's algorithm and backward substitution. We have A as 30 and N as 73. Check whether 30 and 73 are co-prime. The numbers are quite large when we look at 30 and 73, so we can't say if 30 is a prime number or if 30 and 70 are prime number, sorry. So we can use Euclid's algorithm to find the highest common factor with it. When we have those equations 1, 2, and 3, since the second last equation is we have plus 1, so these ones are co-prime. So there is a multiplicative inverse of 30 modulo 73. Rearrange all but the last equation and then apply backward substitution to find integers v and w with 30v plus 73w is equals to 1. V will be multiplicative inverse of 30 modulo 73 since 30v is equals to 1 minus 73w. Rearranging the equation gives these ones. These ones are from the previous equations. These ones, yeah, from the Euclid's algorithm. So you need to rearrange them. After rearranging them, we have that one, yes. Then we do a backward substitution, we get this one. So when we write the equation, the last equation, that is 7 times 73 minus 17 times 30 is equals to 1 as congruence modulo 73 to give multiplicative inverse. Since negative 30 times 30, since negative 17 times 30 is equals to 1 minus 7 times 73, we obtain that negative 30 times 30, negative 17 times 30, congruence 1 modulo 73. So negative 17 is a multiplicative inverse of 30 and modulo 73. We can stop there, but we can also find the least residue modulo 53. Since negative 73 is congruence 56 modulo 73, 56 is also a multiplicative inverse of 30 modulo 73. That has been the lesson for today. Thank you as we proceed to another concept by my fellow colleague. Thank you.